Hello folks, this is one of the videos that I'm preparing for the playlist intended for people who are new to 3D Experience or they're transitioning from the ABAQUS program into the FEA solver of the 3D Experience for release 2022x. The way the playlist works is that I have taken videos from YouTube where tutorials were done with ABAQUS CAE in a step-by-step way and showing all the icons and the clicks and things of that type uh, when it's done on the ABAQUS interface. And I'm retracing those steps in using the interface of the 3D Experiences FEA solver, which is incidentally the ABAQUS program. However, the icons and the interface and some of the functionalities are different. So that is really the purpose of this particular playlist and the videos in it. So this particular video that I'm taking is from this YouTuber's channel, and the link is here. It is pressing of a relatively rigid punch, cylindrical punch, onto a softer material down here. There is some analytical solution for this that is coded down here, but my intention is to not to match necessarily these results, although they're in the same ballpark, but you really have to do a meaningful mesh and a mesh refinement strategy to match these exactly. That was really not the intention. It is assumed that the rigid punch is actually not that rigid. It's actually made out of steel, but the plate underneath it is made of a material that's a lot softer, which is, for example, right here. Remember, for steel, the Young's modulus is 200 gigapascal, and this is 200 times smaller, softer than the rigid cylinder. Okay. There is already an initial gap of 0.2 millimeters here, and we're pushing this thing down by a total of 0.4 millimeters, which means the first 0.2 is going to establish contact. At the end of the first 0.2 millimeters, establish the contact, and then push this thing further down. The problem is done in, with a plane strain assumption, which is not available incidentally in the 3D experience. Neither plane strain nor plane stress are available there. So what I have to do is to solve this thing as a 3D problem, and then trying to make sense out of that. Okay. All right. Here is the results of this YouTuber. We have the displacement. Obviously, this is all blue because it's just translated down by 0.4 second, not 0.4 second, 0.4 millimeter. That's why it's all blue here. But there is the deflection of the plate underneath, and there is the von Mises stress, and that's a contact pressure. Okay, good. The analytical solution. So we can do this problem several different ways as far as the contact goes. We can do it with the analytical rigid surface, which represent that cylinder, rigid cylinder, or we can do it as a punch that is basically a rigid body. Okay, so I'm going to go this route. I'm going to do it as a rigid body. And this being the case, I don't even have to make it a full cylinder. I can make it a tube, basically. Since it's going to be rigid, it really doesn't matter. And this is all done in the Abstractions tab, just to remind you. Defining analytical rigid surface and rigid bodies are done in the Abstraction tab. And obviously, we're not going to do this. So The plate underneath is going to be meshed with solid elements like so, and the details of the meshing is done here. And I'm going to show you in a step-by-step way how to do this. And the cylinder is made of a portion of a cylinder. Actually, you know, this is about maybe I don't know, one 30-degree sector or something like that. Okay, so we don't have to model and model the whole cylinder. Now, because of symmetry, we don't have to model the entire thing. We pretend that this is 1/8 of the plate. Okay, so the other piece is here, and there are two more pieces on the left. So because of symmetry, I'm going to reduce those. And now, when it comes to the defining rigid body, uh, well, first of all, we need a handler point. So instead of creating a point and selecting it, I said, okay, do it at the center of mass of that piece that I'm taking, which is incidentally that portion of the cylinder, which is this dot that you see there, and use center of mass of it. So I'm going to apply my displacement and things like that to that reference point. But also you have to mesh it. If you're doing it as a rigid body, you have to mesh that rigid body. I can mesh it. So therefore the material mesh it and declare it as rigid body. Therefore the material properties of the cylinder are irrelevant. Okay. However, I will use the information that's given to me by the reference. Okay. And the contact is assumed to be frictionless and hard contact. Okay, and that's yeah, this is the material properties. This one is for the punch that I'm using properties of steel, but this is totally irrelevant because as I said, it's going to be declared as rigid, but you do need property because it's going to be meshed with shell elements, and I need the 2D property, so it's needed, material is needed. And the block is going to be, or the plate is going to be modeled with solid elements with the properties that are given, 1000 megapascal and 0.3. Okay. Okay, so let's go ahead and do that. This is a contact problem. It consists of two parts. So I'm going to start with a assembly. So see, I went there and I did go to the assembly design. Okay, all right. So an assembly has been created. Let me, yeah, let, I'm not going to rename these things. It's a good idea to rename them. Maybe I should at least do the first one. So I'm going to call it, well, we're going to call it the date today, May 8, 2022. Okay. Let's insert our first part, which is the plate. So insert, put the cursor there, right click, insert, 3D part, and this is going to be the plate. All right. And we're going to make it. Okay, let's see for a second here. What was the dimension of this plate? It was 50 millimeters long and 2 millimeters thick. Because we're taking 1/4 of that, because we're taking 1/4 of that, it's going to be 25 millimeters long. So on that plane, we're going to sketch a rectangle that is 25 millimeters long, half of the length of that plate, and thickness of 2. This is going to be 2 millimeters. This is the thickness of it. 2 millimeters. Okay. And the length of it, this length is 25. Okay. So there is going to be the representation of my plate. It's going to get extruded. So I'm going to exit. Now it's a plane because we want to kind of compare these things with the fellow's ABAQUS calculation grossly. Okay. and he is doing it in plain strain condition. So what I need to do is to extrude this thing so that it's relatively long. So I think I'm going to extrude it by 20 millimeters. So let's find out. Let's go to the, oh, this is the generative shape design. If you want to make a solid part, you have to go to the part design. And let's go to the essential, and there is the pad, and I'm going to do that by 20 millimeters. Okay, there we are. So this is that plate, a quarter of that plate. Let's apply a material to it. We're going to create a material. We go to Tools, Create Material, call it Plate May 8, 2022. You say OK. Right there. So right click, apply, and I don't need this. I'm going to apply to that plate part. And now we input the results, input the data. So double click on material simulation, structures, ABAQUS multi-physics, mechanical, elasticity, elastic, and this was the plate. So we were told that the Young's modulus of it is 1000 MPa. Okay, and Poisson ratio 0.3. Okay, good. Now that this is done, we're going to go to the assembly, insert our other part, insert another part, which is another 3D part. All right, and we're going to make it. So double click on this. Now, because we're going to be creating a surface, I might as well go to the generative shape design, not the part design. So back to the generative shape design. So on that vertical plane, I will sketch. I don't want to do any assembly constraints. Therefore, why don't I draw this thing in position the way it's supposed to be? So I'm going to make an arc of a circle. So center here and like that. And, go an arc in a circle of a circle. So maybe that much. The actual size is not important as long as the contact establishes between that and the plate. It really doesn't matter. And yeah, let's position these. First of all, the radius of this is 5 millimeters. The radius of the punch was 5 millimeters. So this radius is 5. Sorry, 2.5. No, radius is 5. Yes. Let's see now. Radius is 5. Okay, so that is 5 millimeters. Okay, good. And let's move this thing up. Okay, good. Now we want the distance between this circle, this point, and that top edge is 0.2 millimeters. So let's put a dimension here. Dimension between this point and that. Let me try it again. Normal view, that's better. Yeah. The dimension between this point and that, let me make it 0.2. Actually, I want it to go further up. So let's see if we can move. Let's try this thing. Actually, let's make it cancel that. Let me delete this. this, and we're going to move this point up. Okay, now put a dimension. Dimension between that point and this line, 0.2. Okay, good. So we're going to exit, and extrude this. Where is the essential surface? We go to the surface tab. There's the extrude by 20 millimeters. You can see that. So this is going to be later on my rigid punch. Okay. Let's apply our material. We go to tools, add a material, and this one we're going to call it the punch. The other one was called, I think, plate. May 8. Later on, of course, it's going to become a rigid object, but we need the material for that. Actually, yeah. Right click, apply to this part, and we're going to input the properties of steel, but it's going to be overridden by the rigid condition. So structures, ABAQUS multi-physics, mechanical, elasticity. So that's going to be 200,000. 1, 2, 3. Okay, Poisson ratio 0.3. Good. Let's go all the way to the top and save everything. Assembly and the parts are all going to be saved. All right. The next step is to go to the structural model creation right there, and select an empty FEM. We wait for this thing to pop up, and we select everything. Okay, everything means the entire assembly. We're gonna create a mesh for the entire assembly. Let's start with the block actually. So or the plate. So we go to mesh, and I'm going to do a sweep mesh right here. See that? Not there. Right there. Sweep 3D mesh. Now, if we go back to this screen, you see that it's right here. The size is 1 millimeter, but also I have number of layers as 7. 1 millimeter and 7. Okay, so for the object, we select this object. Oops, cancel. Remove that actually. Okay. Part body. Oh yeah, that's fine. Yeah, this is fine. So 1 millimeter. Yep. Body 1 millimeter. And the number of layers, we're going to make it 7. This is the source surface, and this is the target. So it's going to sweep it in this direction. If you want to do other direction for some reason, then you have to go back here and do the manual source, and then select the appropriate surfaces. But this is fine. Let's check it out. Yeah, that's what I want. Okay, good. All right. Now we're going to do a solid material properties. Properties under solid section. We can select our part body right there. The proper material is selected. Say OK, and notice that we have properties created, and of course the swept mesh also done. Now let's go and mesh the shell. So we go to mesh, and this is the one that I'm using, surface quad mesh. And let me show you the kind of information that I want to use. 2 millimeter, and this is it. 2 millimeters. Okay, so let's go ahead here. 2 millimeter, and this is the let me see what I'm selecting the part body again, part body, and you can select this the surface, it doesn't matter, but I will select the part body and then mesh, and there we are. Okay, if you want to do some visualization, right click visibility manager. Don't show me the part there. So this is supposed to be that. Okay, good. Then we're going to create our rigid body. Oh, wait a minute, the thickness first of all. So we go to the properties, shell section. So you select the trying to see what I chose as the section. It really doesn't matter. So let me go ahead and select the part body. How about that? Right there, proper material is selected, punch. Now this thickness is totally fictitious, so I'm going to put 0.1 because eventually this is going to be a rigid object, okay? Totally fictitious, we say okay. Uh, you have to be a little bit, yeah, that's fine actually, yeah. Good, okay. So this takes care of our meshing. Now we're going to worry about rigid body creation right there. Okay, so let's go here under the abstraction. This is the menu that we need, rigid body, and we select it as extrude. You can also probably select it as part body. It really doesn't matter. There are many different ways of doing these problems. So I'm going to do extrude. And for reference point, instead of me having created something and then pick it or create it now, I can say center of mass. So what it does, it basically make the center of mass as the reference point. It's just you can use any point. You can use any of these corners if you add one, or if you create another point out there, or you can do it right now. That is fine. Okay. So that takes care of the mesh. So now we're going to go to structural model creation, structural scenario creation. Select the finite element model that was created. All right. So we go to procedures, static is a static step, and let's put down initial increment of 0.01 and maximum increment of 0.1. These things in real life, you don't have to experiment with it. So it's not that you can, just pick something and then just go ahead and do it. But I have tried these. These are fine. You can make probably bigger. You can use a bigger maximum initial time increment. You can make a bigger maximum time increment, etc. This time, by the way, is completely dummy. And we include the geometric nonlinearity in the problem because the reference has done it. So we're going to do the same thing. All right. Now we go to uh, restraints. Actually, let's go to restraints. First of all, this is a plane of symmetry, and the side is a plane of symmetry. And we are told the bottom of this thing is clamped because that analytical solution that comes from Johnson's contact mechanics book assumes that the bottom is clamped. And in this fellow's work, he has clamped the bottom of this plate also. So we're going to do exactly the same thing. So here's the clamp, the bottom here, right there. See that? This is what it does when it clamps. No, there's no other identifier there. Okay, now the reference point, which is that center of mass, we're going to push it down only. We won't let it go anywhere except pushing it. Apply a translation to this the reference point of this rigid body, okay? But fix other displacements. So let's go ahead and do a on the restraint fix displacement of this point. I don't want to select the whole surface, So let me uncheck it. Okay, you go here, you say, okay, I want to put it on the FEM features, see that? FEM features. And it's the rigid body right there. See that? It gives you a list of what is it in the finite element features. So select that. Okay, and I want a fixed translation direction x, y, and rotation about y, x, y, and z. And you say okay, and what it does, it actually puts it on there. If you want to see where it is, right there, it placed it. It placed it at the center of mass. Okay. Okay. So where is our load here? Let's apply our load. Delete this. Right. So let me apply my load. I'm sorry, this I inadvertently deleted something which I didn't mean to. Okay, right there. This is the one that I did. Fix displacement. Okay. Now translation to that point. Once again, if you're having issues with this, go to FEM feature, and there's the rigid body that you selected, and you give it a displacement in direction z of minus 0.4. There's two of them here. I can't see where the other one is coming from. Let me see. Inadvertently, earlier I probably put this one. Let me delete that. Right there. Okay. So let me show you what we did. The first thing was to apply a fixed displacement, fixing XY translation and rotation XYZ. So it can move in the Z direction. And to pick that, I went to the FEM feature and selected rigid body from it. Then I applied a translation, a downward translation, which is on the load translation right there. And same thing, I went to the FEM feature, I selected rigid body, I put a minus 0.4, okay, and everything is placed at the center of mass, okay. And the reason you had another arrow pointing up, because inadvertently I had also put another translation upward, which I really did not want. Okay, good. Now, the last thing to do is to create the interaction, because if I run it now, this will go through this. As a matter of fact, to convince you that it will happen, I don't have an interaction defined. So let me go ahead and do that, show you that this actually will go through the part. So let's go to the simulate, do a model check. Good. Let's do a simulation check. And finally, we're going to run it after this is, assuming that there are no messages here. There are no error messages here. But you will see that actually that thing will go through the bottom plate because there is no interaction defined between them. And we're going to come back and fix that. There are some warning messages. A good idea to read these things, but I'll leave it the way it is. Okay, good. And now we're going to run it. As I said, when it comes to applying these displacement and translation to that rigid body, there are different ways of doing it. If I had created a reference point outside of that mass center location, it would have been easier to pick it, but I didn't do it. Here is Here's the iterations. This is the monitor button in the ABAQUS CAE programs called iterations here. As you can see, all these steps, if you're familiar with ABAQUS CAE, all these steps are one-to-one. There's one-to-one correspondence between this interface and ABAQUS CAE, except that they look different. And not everything is available, such as plane stress and plane strain is available in CAE, but not here. I was told that in the recent release R2022x of 3DEXPERIENCE, axisymmetric model has been incorporated, but I'm not sure whether it can do contact problems or not. Okay, this finished. So let's see now. We close this. Yeah, you can see that this is the initial step and this is the final step. It does go through it. See this? It does go through it because there is no interaction defined. These are different stages. If you go further up, at some point it will go through it. You can see that right there. Okay. All right. So let's go back to the standard standard this scenario and create our interactions. Okay, so here's what we're going to do. There's the interactions tab. First, you define the surface-based contact, and let me show you here what I did. This is my I don't think I showed it. I don't think I showed it to you here. That's okay. We're gonna do that right now. All right. This thing smaller. Kill this. Okay. So you have to select the main surface. The main surface in the previous versions of other software were called master, and this one was called slave. So these are changed to main and secondary. Okay. So if I select, for example, extrude, the different ways of doing this thing, if I select extrude, the different ways of selecting these. You remember, if I select extrude from, let's say we do it from the tree, right there, it gives you two colors, okay? The green color must be facing the purple color, okay? So, and if it doesn't, then you use this thing to flip it, okay? So I can flip this. I don't want to because I want the green one to face the purple one that I'm going to pick. For the purple one, I select this. Again, I might have said it in a way that was misinterpreted or can be misinterpreted. I said that these two have to be pointing in the same direction. That is really not what I meant to say in another video if I did it. What I meant to say was that the green color must be facing the purple color. And if it doesn't, then you flip these so that it does, okay? And now, obviously, if you look at this, yep, it faces it. If not, then you go here, click on it until it faces it. This is not right, okay? Okay, good. So we say okay. And now the nature of the contact property, you click on it, and this dialog box is actually that one, okay? So let's go ahead and do this. Tangential, specify behavior, but zero friction. Okay, if it's not zero, then obviously you have to put the right number, but zero, doesn't matter whether you select this or not, it's right there. Normal, you're going to specify as contact, and this one is just default. So we have specified our nature of interaction. Okay, so we go to simulate. I'm not going to bother with these because they I don't think that they made a change so that it affects these. But if you want, you can do a model check and then a simulation check. But I'm going to take my chances and run it. Incidentally, you know that if things don't converge at some point, you still have the results before that, and you can go and look at those results. Okay, I made it clear in the other video segment that I did on uh, again transition playlist when I was doing the dog bone example. This is almost reaching the end, halfway through. This time, this time contact will be established, and it will press that bottom plate. Okay, so extracting, soon it's going to be extracting results. Okay, there we are. So if you animate it, you see that it starts from the top. You can slow it down here. So we go there. Don't go to set the speed. Uh, Slow it down. Oh, you can see that. Now this is one Mises stress contour, and you can do the. Let me get out of this. This is one Mises. At what stage is that though? This one is initial. So if you go all the way to the end, then the compression has been done. If you want to do the contact pressure, you change this thing to contact. Contact pressure is down here. And see that contact pressure is shown. These numbers don't match with the theoretical result because I don't know what kind of a mesh the fellow used in ABAQUS, and also uh, really to be confident about the numbers, you have to do a mesh conversion study to make sure that this mesh is actually appropriate for the comparison with the analytical result. Now, just to convince you that the direction of that blue, green, and purple surfaces are important. So I'm going to go to the interaction right here. See that? I'm going to go to the interaction, double click on it, and I'm going to change this. Okay, change this thing so that the green does not match the uh, yeah, does not match the purple. The green is on this side, purple is on that side. They don't match. So we say, okay, notice that I did it so that they don't match. Okay, let's run it and see what happens. And if everything goes well, this actually will penetrate through that bottom plate. I think it's worth giving it a shot. And it just happens that in this particular problem, that those two arrows are chasing away from each other. It just happens. But sometimes they may point towards each other, but still it penetrates. It has to do with, are the green and purple surfaces mating? Not necessarily with how those arrows are. Those arrows, one of them will allow you to flip, the main surface's direction. Almost done. This is the plot, the simplified version of the iteration or monitor in ABAQUS, extracting the results, and lo and behold, this is going to go through it. Yeah, let's actually look at the displacement. Yep, it did go through it. Let's change the speed here. Right there. Okay, good. I hope you found this tutorial useful. I could have done this problem as an analytical rigid surface, but I'm sure you, by watching some of the videos that I posted, you can do it yourself.